Ya, listo. Uh, I will be switching to English because that's the only way I know how to give this presentation, actually. So welcome, everyone. My name is Sebastian. I'm an undergrad from Universidad del Valle. I will be graduating later this June, and I will be showing you a brief part of my thesis defense that I did in December. So my thesis was titled "Implementation of a Numerical Method Based on Tensor Networks for the Analysis of a Lattice System of Spin-1 Bosons Under the Influence of a Zeeman Magnetic Field." It's quite a mouthful, but long story short, I used a numerical method called Tensor Networks to analyze a one-dimensional system. That system in particular was the Bose-Hubbard model. So, hopping over, I will showcase, first of all, the outline of this presentation. We're going to start by the why, showing you a bit of the quantum many-body challenge and why we're interested in developing numerical methods to study these type of problems, as well as the dimensionality problem. Then I'm going to show you how we did it using tensor networks and how we implemented it from scratch using C++. And finally, I will be showcasing some of the results tailored to the Spin-1 Bose-Hubbard Hamiltonian. So, starting for the quantum many-body challenge, one of the problems in dealing with quantum many-body physics is that the number of available states that we have grows exponentially with the number of particles that we have, as well as with the physical dimension of the system. So if we have electrons, for instance, we will have a dimension of 2. And if we wanted to calculate using a classical computer, we want to calculate the interactions between 74 electrons, we'll have this number of states, 2 to the 74, which is around the number of transistors that there are in the world. So it becomes unfeasible to think about measuring or making calculations for even a small type of system, because we're looking at real states. Real materials would be looking at the number of Avogadros, so 2 to the probably 100 and something. So that's quite way more than we can actually calculate by doing it in a brute force type of way. And if it was the case that we wanted to calculate using only spin-1 bosons, for example, we will have a physical dimension of 4, which increases our problem by orders of magnitude, like a lot of orders of magnitude, only using one boson per side. In this case, we do 2 bosons per lattice side, and our physical dimension with the degenerate entire basis is 16. So we have 16 to the 74 power if we wish to calculate that number of sides. And the problem becomes unfeasible. That's why, which is roughly about the number of protons in the universe. But Richard Feynman once said that if you wanted to study the nature of these types of quantum systems, you shouldn't be using a classical computer. You should be working with something that is quantum in its very nature. But we're going to show that using tensor networks, we are able to calculate these types of systems without any loss of generality. So, bringing that over to the real world, we use cold atoms, ultra cold atoms, which are atoms which are cooled by using plenty of methods. The one that we're going to be focusing in, just for the example, is laser cooling, in which you have, in this 3-dimensional case, 6 types of contrapropagating lasers, which makes a 3-dimensional lattice. And so the atoms are confined to a certain space, which and they are not free to move in freely to say, but in only 3 dimensions. That is also the case for 2 dimensions and 1 dimension by using less contrapropagating lasers, and that brings a lot of rich physics to it. The atomic, molecular, and optical physics community are really interested in, they are all working in these types of systems, and if you can see how is the movement discretized between sites in 3 dimensions, you can see that particles can move uh, a lot of ways, roughly up, to the right, to the left, and all of them. And you can also have these types of movements in 2 dimensions. But the interesting case appears in 1 dimension, where they are not able to avoid each other. So if they're hopping around the lattice, they are bound to interact in one moment or the other. And these avoidable, unavoidable interactions is what makes 1 dimensional systems so rich in physics. They bring a lot of rich physics regimes, which namely are multi-insulating regimes and superfluid regimes for the Bose-Hubbard case. And precisely because of the low dimensionality, we can simulate it using tensor networks. And that brings me over to the tensor network representation. So to get to know the tensor network representation, we first gotta um, understand some of the notation. We use something which is called the Penrose notation, in which we represent numbers as little blobs with legs. So here we got a scalar, which is just a circle with no legs. Then we have a vector, which is a circle with one leg, a matrix with 2 legs, and then uh, a rank 3 tensor, which would have 3 legs. This way, we can not only represent these tensors, but we can also represent contractions between the tensors. Here, we're showing a contraction between the I tensor, I leg, I'm sorry, I index, and we end up with a new tensor. And we can also do a bunch of other operations, namely, for example, singular value decomposition, where we can deconstruct one tensor into 3 other tensors, which have a lot of different characteristics between one of them. Namely, the middle tensor would represent a diagonal one, where it has the singular values, a diagonal matrix with singular values, and these other 2 matrices, the yellow one and the purple one, are also diagonal or orthogonal by either rows or columns. So in Penrose notation, you would have that the product of these two would follow the following relation, where the product of the matrix and its conjugate would result into an identity matrix. And then I'm going. This is a bit of DMRG and why tensor network works, despite the fact that there are so many states in our Hilbert space, and it is because out of the 16 to the 74 power that I showed before, those being the number of states that we have in our Hilbert space, we don't need all of them to calculate the relevant uh, to the physics states. So only a fraction of those states follows something which is called the area law, and it's where the entropy of those states grow as the boundary of the subsystem, which is like contained within a bigger system. So we're interested in the states whose entropy grow as the boundary of this region over here, and that region happens to be really small compared to the entire space of the Hilbert space. And so they, as I have written right here, they scale as the area, as the boundary of the area, instead of the volume of the bulk. These were was so interesting to us that we managed to make an article and publish it in the engineering journal of Universidad Distrital, and you can see it over there if you're interested in reading it. There's a lot of tensor network representations. The most popular ones are matrix product states, as well as projected entangled pair states, also known as PEPs. There are some more representations, such as street tensor networks on the bottom left and Meras, but they are used for more uh, complex problems, such as in open quantum systems, for example. And in this work over here, we're going to be focusing on the 1 dimensional case, which is matrix product states. It begins as making the separation between two systems, a system which can be decomposed in two subparts, but which is entangled, which means that we cannot represent the entire state as just the tensor product of the two subspaces, but as a superposition of the two. So as you can see over here, and this tensor over here, the a sub ij, can be represented as this in tensor network in Penrose notation, where you have one single blob with a bunch of legs depending on the dimension that you have, or the rank of the, I mean, the size of the tensor network. And so we get from this bipartite system to a general state in where we don't have an actual separable state, in which the same case that I showed before, where you actually work with a superposition instead of just working with the uh, single representation of each state. And we end up in this representation over here. You have here the coefficients with which represent your whole lattice, one-dimensional lattice, and via doing singular value decomposition and regrouping a bunch of tensors together, you can end up with this representation, which is a matrix product representation, in which these A tensors, which have a physical dimension of n and a virtual dimension index alpha, have all the information of the one-dimensional lattice, and each one of these A's represents one lattice site. And that's how we get to the matrix product representation. You can also represent its conjugate just by flipping the legs over, and that's really cute, really nice. There's a bunch of mathematical rigor behind it, but because of time, I won't be showing it here. And I wanted to show you also how we implemented it in C++, because it sounds really nice to be able to represent single tensor, single lattice sites, but the way we represent it in the computer, it's quite different. There's a bunch of libraries which you can use to represent tensor networks and play with them, but we decided to go with a scratch procedure because we didn't understand tensor networks at the time, and we wanted to know how exactly is this physically realizable. And we take this first tensor A, which has three different dimensions, so a rank 3 tensor, and we flatten one of the tensors, one of the index, I'm sorry, to make it two-dimensional. So we take something which is three-dimensional and we make it into something that's two-dimensional. So basically a tensor, from a tensor to a matrix, which can be represented using a simple library such as UVLAS in C++. And here's how it looks like in the computer. So here you have the physical indexes, the virtual indexes, I'm sorry, alpha, and you have each color shade representing one of the different physical dimensions. So if we would have a Spin-1 system, this first one over here, depending on the programmer, would mean like spin -1, then spin 0, and spin 1. And here in the virtual indexes, you will have like the entanglement measurements. So in each one over here, you will have either, if it's the different representation that you decide to to show for your problem. So it can be either the Fox occupation basis or the magnetization basis, which we use in our problem, or any other type of basis representation. You can use it for a tensor network. So you must decide which one of them is more useful to you. And then that being the case in which we represent the physical lattice site, you can represent the entire lattice in this big A matrix, in which after hopping over the lattice sites, you can find the information for each lattice site. You can see over here, it has this chi measurement, which is the dimension of the MPS also called bond dimension, and you have these chi times L on the bottom, which is basically the size of the entire lattice. So you change over here some parameters. The MPS bond dimension, the dimension of your system, which is depending on what kind of system you're working with. Either it's fermions, anions, or bosons, and then you have the total number of sites. And here's how we do contractions. We take the matrix representation of the operator, just as you would in any other quantum mechanics class, and you do the product between each site, each sub-matrix that represents the physical subdimension that you're working with. So -1, 0, and 1 for spin 1. And you just add it into a new matrix. So that would mean like having a contraction between your operator and your site. And then after that, you can flatten that tensor altogether to be able to do a dot product between that tensor and its conjugate, and to be able to contract that as a whole. What you're left with, it's something which is called uh, a transfer matrix. This transfer matrix, it's something which carries all the information about that specific site, and something really nice about it, besides the fact that it grows in it's a tensor which grows in rank. Now we don't have two separate rank 3 and rank 3 tensors. Now we have a rank 4 tensor, and we must reshape it in order for it to make sense physically. So we get uh, the information which is like has faithful representation to the information on the sites that we had before, like to recover information, if that makes sense. But by doing the product of these tensors and getting the transfer matrix, we can get a lot of different things. And that I'm going to explain why we actually care about these transfer matrix. And is that with that and having a different representation of the MPS right here, as we can have an orthonormal representation where you have a orthogonality center here in the middle, or whenever you want, wherever you want it in the lattice, and you can actually calculate expectation values such as operators or correlations, and you can see how they behave throughout the lattice, and that's only by doing the trace of the transfer matrix. In this case in particular, you can see based on the laws that I showed you before, in where these types of matrix behave, being that they are orthogonal matrices, they become ones, and then if you want to calculate an operator that's just in the middle of the lattice, you only have to care about the transfer matrix of the middle instead of just calculating all of these contractions, and that saves you a lot of computing time. So the way it would look like, only using the MPS formalism and represent the operators in this way, is that you would contract this as a whole, make it into a transfer matrix, then trace these two indexes in the left, and uh, that brings me over to something else in which you don't actually have information in these two legs at the beginning of the lattice, neither at the end of the lattice, because these virtual indexes are dummy indexes, in which the way they have information here, it's not actually actual physical information, as we are only putting there just for the rank to be consistent throughout the whole lattice. And so here in the leftmost tensor, you can see that this information in red is not relevant at all. And for the tensor in the most right, uh, there would be no information here in these parts. So only in the rows here, in the first row, and then only in the columns in these other tensor. And then that would mean that we have transfer matrices which have information only in these sites. So in the ones that are not shaded in red, for the left and the right. and that would help us optimize the way we contract these types of of networks in a way that we are not doing operations which are uh, giving us information which don't matter anyway. So going back to the procedure, you would trace over these degrees of freedom first, and then you would contract the following side, and you would do the contraction between these two tensor matrices, and the way that you have already um, exchanged them together. So you made the previous representation that I showed before, like here, you have reshaped it, and now with this representation of the right, you can make the product between two transform matrices, and the results would also make physical sense. And you can see right here, you will have to contract these two and then do the product of them together, and you would end up with another transfer matrix, and you would repeat the process until you're left with nothing but a single one. And after tracing that, you would get the expectation value of this MPS with an operator AI, which is being applied throughout all of the sites. Another neat thing about the tensor network representation is that you don't also have matrix product states, but you also have matrix product operators, which can be applied to any type of operator without loss of any generality. What that means is that you can have any type of non-local operators acting throughout the lattice. So as you can see here, we have the representation of one Hamiltonian, which has neighbor operators, which act in the sites A1 and A1 plus 1. And then we also have a local operator, which acts per site. And you can make this calculation by just doing the product of these W matrices. And you can see it over here, which is a matrix composed of matrices. And this is one of the things that we did manage to do during my thesis work. We were working in a script from my supervisor, which was very old, back in 2010, when MPSs and tensor networks were like getting established, and the use of matrix product operators wasn't so famous as it is now. And so here's a different perspective to it. Another detail that I had to mention, and it is that the first and the last tensors of these matrix product operator or MPO have these different representation. They are not in the as in the green shaded one, but in the red shaded one. So one um, one row vector with an identity in the last place, and one column vector with an identity in the first place. That just to get back these summation representation of the operator. But these two representations are equivalent. And so yeah, we managed to make this using the previous script that was done in C++, and we managed to get pretty nice results. So what's the difference? There's no much difference between the two of them if you're talking about local operators, AI, I mean, i.e., the fact that you can apply like C operators or SC, SX, or SY. But when you are looking at uh, some of these multi-site operators, such as hoping or such as I don't know a time evolution gate, you have to make this representation as this, and you have to make the gates, which is a pain in the ass, and you would also have to come up with a different contraction scheme, which is optimal for for this type of case. But by using MPOs, you discard that altogether, and you only care about the contractions of uh, these rank 4 tensors and the MPS. So the construction is way simpler, and also you take way less time by contracting. So if you have these sites and you have chi bond dimension, you have that the way these contract and the information it has, it scales linear with the size of the system instead of exponential, as is the case if you were to use like a generalized operator, which is constructed all over the lattice. So one of the problems that it carried was that you would have rank 6 tensor, a 6 rank tensor instead of a 4 one. And numerically, that was a problem which was really interesting to tackle, like really interesting. Because in the first representation, you would have something which is like this way, in which you have a matrix with size chi and then times chi d. But if you wanted to do the contraction between this MPO and the physical side, you have something which is W to the second power, bigger than the ones before. Why W to the second power? Because that's the size of every single operator. I mean, all the different items or operators within this W matrix. Oops. Based on the fact that plenty of the of the places within these W tensor are zero matrices, as you can see over here. These square part over here are just zero matrices. That means that in that operation, in that contraction, here we don't have uh, op- like occupied sub matrices. There are some which are completely filled with zeros. That means that when you have the generalized transfer matrix, you would only have information in these first column and last row. This part over here would be filled with zeros, and that's really nice because that carries another interesting thing is, and it is that in the future, if someone wishes to continue with this work, they could also optimize the way we're constructing things by only choosing to do an operation which is tailored to doing the product between these two parts over here and the following transfer matrix, and not and ignoring these data as a whole, because that would speed up things a lot. And our way to approach this part in particular was using a vector, I mean a matrix vector, if you wish to call it, which only has ones in these parts, uh, not shaded in red. And that way, we can make the contraction in the following way. So you end up by calculating the contraction between the first tensor of the lattice and then the operator, the matrix product operator, and then you would calculate the transfer matrix. You would contract this new vector matrix over here to trace over these degrees of freedom of the left. These two would create a new tensor which has the same dimensions as a tensor. I mean, as a vector which traces over the transfer matrix, and you would uh, keep doing the process until you have swept all over the lattice, as you can see over here. And at the end, you would only trace over these degrees of freedom, and you would get your expected value. Hopping over, because I've spent a lot of time over the numerical, I'm going to hop over to the physics of this problem, which is regarding the spin-1 Bose-Hubbard Hamiltonian. Here you have the regular spin-1 Bose-Hubbard, the regular spin-less Bose-Hubbard Hamiltonian, in where you have three terms. The hoping term, which takes into account that we have particles that can move along the lattice, and then you have the chemical potential, which will be responsible for the amount of particles that we can have in the lattice itself. So whether or not it's more uh, expensive energetically to have a particle or not have a particle, and then you have an on-site interaction with which is just a contact potential. It has two remarkable phases in the spinless case, which is the superfluid regime and the multi-insulating regime. In the superfluid one, you have that this kinetic parameter over here, here known as T instead of J, that you can find it in some papers. It's way greater than the interaction. And that means that the particles can move freely. It doesn't matter how many there are in each site. And here, we also have the multi-insulating case, where the interaction term is way greater than the hoping term, so the kinetical parameter. And so there will be a set amount of particles per site, and there will be no movement between them. But when we study the spin 1 case, you will have to take into account another thing, and it is that you not only have the creation and annihilation operators, but you would have creation and annihilation operators for each spin projection. So you would end up with uh, 6 different operators instead of just two, and you would have this representation over here where we have sigma as the spin projection. Another thing that we added, it's Zeeman magnetic field, which has uh, just for lifting up the degeneracies between the dispersion relation. As you can see over here, here you have the dispersion relation for each one of the different channels of spin. And as you can see, as we increase or decrease the number of the strength of the magnetic field, these channels get uh, not degenerate. So they become not degenerate, and that's really nice because now we can explore different regimes uh, based on the amount of magnetic field that we have. Another thing that appears, given that we now have more channels for interaction, is a new interaction potential over here, in which we have the same contact potential that we had before, but now we have to do the projector of each spin channel, and this was not done before. Here you have something, a coefficient which is characterized by the scattering length, A sub s, as well as the mass of the boson itself. And we will be continuing all of that into coefficient G sub s. Here, to make the interaction potential, I mean, to make the interaction term, we will be focusing on symmetric states, which are even instead of odd. So if you exchange the particles between them, you would get a symmetric state instead of an antisymmetric one. And this is basically because we are working with bosons, and we are not caring about any other type of physics at this time. So we end up, after doing a lot of calculations, with this interaction Hamiltonian, in which you have two main interactions. The first of them is spin preserving collisions, in which you start with spin 1 and -1, and they interact with each other, and then they end up with either exchanging spin or remaining the same way. And you also have spin changing collisions, in which you have two starting spins, for example, 0 and 0. They interact with each other in the same site, of course, and then they end up with different spins, 1 and -1. They, of course, have to preserve the total spin before and after the interaction, which, if you want to check for yourselves, every single term here, if you sum these two spin projections, they equal the sum of these other two spin projections. And so our final Hamiltonian spin 1 Bose-Hubbard Hamiltonian would look like this, in where we have the interaction or Zeeman magnetic field, the chemical potential, as well as the Hoping term. And that would make everything. So the representation of the matrix particle operator of this Hamiltonian in particular would be as following, where you see that most of it's composed by the amount of Hoping term that there is. So one row per spin projection, and either if it's a creation or annihilation operator, and then you have all of this term, which is local, and only occupies this last corner of the matrix particle operator. This is something really nice because you can now get more different interactions, and they would just mean that either this term would have a different value, or the size of the matrix itself would change. So you can explore uh, so many others regimes of physics this way. And if you wish to know about like neighbor interactions, like first neighbor interactions or second neighbor interactions, you could also do it this way. And now moving over to the results. Uh, First, we decided to study the Mott insulating case, which nicely enough only has 4 different states. So a vacuum, not having any particle, then a particle in spin -1 projection, spin 0 and spin 1 projections, and the nice thing about that is that you can map the spin-1 Bose-Hubbard Hamiltonian into the into an effective Hamiltonian, which happens to be the Heisenberg, the bilinear biquadratic Heisenberg Hamiltonian. And it takes this representation over here, and it has a lot of subphases, as you can see, just by varying the parameters theta and the uh, magnitude of the magnetic field. And this is the map of these. This is the phase map of this Hamiltonian in particular. So for the first side, the first state that we're going to be analyzing, we have the large T, which is the Ising nematic phase. And the first thing that we studied was the population of the state. So as you can see right here, you have the populations for the -1, 0, and 1 states, particles in the system per site. And we studied it for 30 sites. These had a really nice objective, which was comparing the script that we had before the our work and after, just by doing the comparison between using the MPO representation as well as just the MPS representation as this population operator. It's local and should be giving like the same results, should be yielding the same results, and that's basically what we found. And now moving over for the correlations. There's two types of correlations that we're going to be studying. The first of them are transversal correlations, which give us a lot of information of the system regarding either the behavior because of spin-1 physics, so the polar spin coherence and propagation of spin in the lattice, as well as this other type of correlation, which is S plus S minus but quadratic, which has information about quadrupolar coherence as well as double spin flips. And then we have longitudinal correlations, which give us information about either if it's ferromagnetic or antiferromagnetic, and also the density structure of the system. This is the way we calculate it using Penrose representation. And for the previous MPS representation, and here's how we do it using MPOs. So just one identity matrices in the middle, and then these two matrices over here, in which actually yields the two operators which we wish to calculate the correlation with. Here's some of the results that we got. As you can see, they are decreasing exponentially, which is what you would expect in a Mott insulating case, in where the information is not being communicated between sites because it is an insulator, so it is decreasing exponentially, as you can see, for the three different correlators. Then we also repeated the same procedure that we did before, but using different ground states for these different parameters. So we ended up calculating the population for the XY ferromagnetic case, the dimmer nematic, as well as the large D ferromagnetic. And you can see right here that there's different behavior between the population density of the lattice, favoring mostly the zero population. This is just because of the type of magnetic field that we're putting in this model in particular, which instead of being linear was quadratic. And that's why the population of spin-1 and spin-1 are not favored whatsoever, and they are behaving like sort of in the same way. Then you can see the different correlations between phases. As you can see here in the first one, uh, which is for the XY ferromagnetic, the correlator in all three of them is positive, and it is large by decaying really slowly between all of them if you compare it to the other ones. And uh, this is because the slower it decays, it has a long correlation length, in which, well, now it is communicating, like it is interacting between sites a lot. It doesn't mean that they are hopping between each other, but it means that the information is going to be communicating around the lattice. and this is expected as the magnetization lies in the xy plane, and this is a transversal. Um, these two, for example, these first two columns are transversal correlators, and this is giving us a lot of information about the fact that it is a paramagnetic phase. Um, then we have the these large T ferromagnetic, in which we see the spins frozen. That's basically what we see over here in the double spin case, and that's basically what's expected between because it is suppressing transverse spins fluctuations. The fact that it is in the large T case, and another really nice one was in the dimmer, which this phase in particular is something that's um, native to the Spin-1 system. It cannot be achieved using fermions. And here, what we are interested in is the fact that there is clear damped oscillations. As you can see, it is not following a clear exponential decay, but a damped one, and that basically means that there is no ferromagnetic ordering, and that quadrupolar fluctuations are dominant. And then we have the more interesting case, which is a superfluid one. In the superfluid one, what is the biggest challenge is basically the fact that the size of the basis grows by 4 times as much as we had before in the one particle example. Uh, and that means that we have 16 different basis states. As you can see, there's some which are degenerate. As you can see, the first column and the first row, there are a bunch which should be the same, and this is something that can be optimized later. But we decided to work with this general case to see how much we can push our code. And these are the parameters for the ground state that we calculated. Something which I have to mention is that for this system, because the physical dimension is so large, the program or the script that we used to finding the ground states with was a DMRG script, and it took up upwards of 25 hours using a pretty decent computer here at Universidad del Valle. So just because of the size of the system, you have to work with systems which are like of fewer sites. For example, here we used 8 and we vary it afterwards. But the important thing is that the bond dimension of the MPS must be greater or equal to the physical dimension of your system. Um, Here we have other parameters that we used for the hoping term, the magnetic field, as well as these interaction terms. We studied two subphases, the ferromagnetic and the antiferromagnetic one, and we can see over here the contrasted results between the script that we had before and the one we have right now. And as you can see over here, the calculation of these operators yielded the same results. One thing, and you may be wondering, why is this guy showing me the expectation value of the density of the sites? And it's basically because we're interested in seeing these abnormalities here, and it is the fact that the system does not have um, a symmetry between the number of sites. There shouldn't be an appraisal of a not symmetry like this. So there should be a mirror symmetry between the middle, the left branch and the right branch of the lattice. And the fact that we are not seeing it is telling us that we have not actually reached the ground state of the system. And that can also be shown here in the variance. But if we are not seeing something which is characteristic of the ground state of the system, then are we actually in a superfluid regime, you may ask? And to be sure that we're not in a multi-insulating regime, we calculate the variance of the density in each site. And the fact that it is non-zero reflects the fact that we are not in a multi-insulating regime. So this gives us a little bit of reassurance in the things that we are calculating right now. Uh, Here we have the correlations where we managed to calculate we, to, uh, we managed to calculate them, and one interesting thing is about uh, this last correlation over here, the SZ correlation, in which you can see negative values at the ferromagnetic case, the no, the antiferromagnetic case, and also a damping behavior. And it is because of the complex values in the transfer matrix. So, as the same way that we were seeing it before in the Mott insulating case, we do have it in the SZ for the superfluid regime. We also managed to get our hands in a supercomputer in the Okinawan Institute of Technology, thanks to a partner of mine that we were working together in the thesis work, and we managed to use it to calculate in parallel a lot of different ground states. Unfortunately, either there's something wrong with the code, or straight up we were held up in a stationary state, because after doing the calculations for these systems where we vary the size of the lattice as well as the bond dimension of the MPS from 12 to 60, we only got some states to converge. So as you can see here, these which are colored have the our actual physical states that we got, but the ones that are blank are in states which didn't converge. So we only have a handful of states which converged. But here, what we are seeing is that it's something really interesting, and it is the fact that these states are not behaving the way a regular superfluid regime should be behaving. And that is basically because we are not seeing a behavior of decay which is algebraic. Instead, we're seeing something which is decaying exponentially. So here we can see in this heat map the way these different correlation lengths are varying uh, depending on the amount of bond dimension of the MPS as well as the size of the system. Um, what's particular here is the fact that we took all of these states and we plotted the correlation lengths against the number of states that we had. And what we found is that there's a point in which it doesn't matter how much you increase the size of the lattice, you would end up with the same correlation lengths that you had before. And that is really interesting because that gives us the information of when you have reached bulk behavior for certain correlators. And that would make it more feasible to find uh, the ground state of certain states which are not higher than 19, which I didn't put over here, I'm afraid. But up from 19 sites, you would get the same correlation length. So if you're interested in calculating correlations and you have a total total network length of 19, you would be more than good with this model. Then we have the conclusions and the perspectives of this work. First of all, um, we made a physical framework for spin-1 lattice bosons, and this was tailored for the spin-1 Bose-Hubbard physics under a linear Zeeman field. And we identify how tunneling interactions and spin degrees of freedom give rise to distinct behaviors. Then we implemented a transparent tensor network toolbox in which you can take our script and implement another Hamiltonian, change the physical dimension of the system, and you can calculate uh, you can measure a lot of different operators using the script. And we validated it by using non-trivial applications for both the Mott and superfluid phases. And for the conclusions, we have first of all that a modern and reliable numerical infrastructure was established by expanding the previous script from Karem to something which implemented the matrix Barak operators. Then we managed to characterize the spin-1 Bose-Hubbard physics successfully, although we didn't get the ground state that we were expecting for the superfluid case. And finally, this work opens up a future uh, branch within our research group here at the Universidad del Valle, in which you can now see people. There's a couple of guys now working in algorithms and different problems. So there's a lot to do next in this work, mostly regarding the time evolution block decimation algorithm for this library in C++, and also different DMRG algorithms using MPOs, which has not been done before with the script that we currently have. Then we have the speed up of the contractions by using CUDA, which is a package managed and developed by NVIDIA, and also doing the benchmarking against different tensor networks libraries, such as the tensor network library, which was developed by Frestrata, the other tensor network library, which is developed by NVIDIA, and then another package for Julia called DMR Julia. Also, we have the implementation of periodic boundary conditions, as well as mapping the phase diagram of the Spin-1 Bose-Hubbard model, are two things that we think that can bring a lot of new ways of analyzing this problem. There's a lot of people that are interested in Spin-1 half physics, but there's a few of them which are interested in Spin-1 because of how big the physical dimension grows and how these libraries over here are basically black boxes for the ones that are caring about the numericals of the situation. Finally, I gotta thank my supervisors, Dr. Carmen Rodriguez and Andres Felipe Galindo. Without them, this work would have taken uh, 5 years instead of two, and they're basically the responsibles for this work being so nice. And thank you for listening, and that would be all.
Ok, muchísimas gracias, Juan Sebastián. Muy interesante. Ah, yo tengo un par de preguntas, pero no sé si yo quiera empezar de primero, si hay alguien más que tenga alguna pregunta, algún comentario. Adelante, Santiago. Ujú.
Hola, sí a todos y todas. Buenas noches, espero que estén muy bien. Sebastián, muchas gracias por esa charla. Estuvo increíble, está muy bien hecha y refleja pues muy bien el trabajo del grupo. Quisiera preguntar acerca de por qué cuando tomaste la fase del Mode Insulator, teniendo en cuenta que se trabaja con una partícula por sitio, consideraste también el vacío. ¿Es necesario numéricamente esto o es por alguna condición física que estás tratando en el sistema?
Gracias, Laura, por la pregunta. La razón por la cual estoy mostrando, es más, déjame ver un poco porque no sé si sigo compartiendo, no estoy muy
Sí, sí
seguro.
estás compartiendo.
Ok, entonces voy a intentar volver a esa parte de la pantalla porque no la veo. Ah, no,
Creo que
espérenme,
fue
dejo de
justo
compartir.
antes de comenzar a mostrar los resultados. Tú
Sí,
mostraste el mod
sí
pero
sé
no
en dónde
tampoco
estás
re...
diciendo. Déjame un momento, comparto toda la pantalla porque
Dale, dale.
acá, acá es en esta parte, ¿no? Esta parte
Exactamente,
acá,
sí.
listo. Es básicamente acá estoy mostrando que tenemos en el mod insulating regime hay cuatro posibilidades, ¿no? No tener una partícula o tener una partícula con tres diferentes proyecciones de spin. Pero el hecho de que tengamos tres quiere decir que se puede, o sea, que solo tengamos una partícula por sitio quiere decir que se puede mapear a este otro Hamiltoniano. Y acá, de hecho, en este Hamiltonian no tengo en cuenta el vacío, solamente tengo en cuenta estas tres dimensiones físicas. Entonces, corto acá de 4 a 3.
Ah, vale, vale, vale. Súper. Gracias. Y bueno, la otra pregunta que sí es curiosidad. eh, pues en este método numérico que ustedes desarrollaron, tú en el sistema tomaste condiciones de frontera abiertas, ¿no? Sería muy complicado implementar eso con condiciones periódicas en la frontera? ¿O
Fíjate que ahí hay una cuestión, y es que la manera en como nosotros lo representamos numéricamente sí son abiertas. Para pasar a condiciones periódicas, había un salto como numérico que había que hacer, el cual nosotros no tuvimos la cabeza de hacerlo a la parte final del trabajo. Pero creo que ahorita mismo Iván está trabajando en un problema que requiere implementar condiciones periódicas de frontera. Entonces está utilizando ese script para hacer eso. Pero eso ya es otro trabajo de grado.
listo, Sebas? Muchas gracias.
Gracias, la
Bueno, y vi que Karen también nos está acompañando. Gracias, Karen, por estar acá. Ah, no, o sea, Juan Sebastián, yo tengo aquí preguntas, un poquito de Lego, pues de principiante aquí con esto. Con la representación que nos estabas mostrando de tensores para los operadores que nos estabas diciendo que escalaban mucho mejor, ¿no es cierto? Que escalaba, por ejemplo, lineal con L y no exponencialmente con L. Creo que es más eso ahí. Y luego tenías, pues, cómo expresabas estos operadores, por ejemplo, X más S, etcétera. Exacto, aquí arriba en la 93, ahí la estoy viendo. Ujú. Digamos, una pregunta que yo te tenía es, ¿qué tan expresivo es eso? Uno siempre puede expresar así de bien escalan cualquier operador que uno se imagine.
Así, a priori,
Ujú,
como para responderte y no dejar con la pregunta al aire, sí, cualquiera. O sea, tú puedes colocar cualquier tipo de operador, así sea uno que esté operando en el sitio I y el otro en el sitio I más N, cualquiera
ujú,
de esos operadores se pueden hacer. Y de hecho, complementando con la pregunta de Olave, en la literatura no está muy claro la descripción numérica de el hecho de que haya condiciones periódicas numéricas de frontera para la contracción del MPO. Hay unas cosas que son necesarias hacer con el primer y el último tensor, pero también se pueden representar como periódicamente estos dos tensores de acá. Entonces, para que interactúe, digamos, si son de primeros vecinos, que este X sub 1 interactúe con el Y sub n, por ejemplo. Entonces, ahí hay otro tensor que tiene que agregar para que al hacer la contracción termine con ese, ese término.
ok. Bien. Ah, solo otra para yo estar como tranquilo de que más o menos seguía ahí hasta el final. Cuando nos estabas mostrando ya en los resultados que tenías esta parte de la superfluidez, que nos estabas mostrando pues las fluctuaciones al final del número de partículas por ciclo, ¿no? El que estabas
Sí,
mirando
ajá.
ahí. Exacto. Entonces ahí, digamos, el argumento es que esto realmente es superfluidez porque no está en la fase de aislante, ¿cierto?
Básicamente, por ver de que escuché, no estamos en una fase de mod por el hecho de que la varianza es cero. Tampoco podemos decir que es un régimen de superfluidez, o no estoy como, no tengo la certeza de que lo es por el hecho de que las correlaciones están decayendo exponencialmente y no algebraicamente, como debería ser
Mm,
en el estado superfluido. Pero
ok,
tampoco
sí.
estamos en la mod insulator. Entonces ahí estamos en un lugar extraño que seguro tenga problemas por la convergencia del estado base.
Ok, pues bueno, yo no sé, yo no tengo más preguntas. Esto a mí me alegra muchísimo que estén en el grupo de ustedes investigando en esto con tanta fuerza. Tal vez una pregunta que seguro te la hace todo el mundo cuando ves y tú arrancaste a hacer el código desde cero, digamos, desde abajo. Ah, ¿qué tan necesario es hacer esto? ¿Por qué no usar las librerías que ya estaban ahí de Tensor, de tensores, pues todas las que hay ahorita?
Listo,
Tú
esa
ahí
es
igual mencionas al final también en las perspectivas, en algunos cuadritos pones ahí algunas de esas.
sí, acá. Sí, hay muchas en realidad. Pero el problema es el hecho de que la gran mayoría están hechas en Python, y cuando tú intentas incrementar la dimensión física de tu sistema, es decir, cuando ya pasa de ser de 16, de 2 para el caso de fermiones a 16, ya empieza a encontrar muchos problemas de performance en esos programas. Entonces,
Entonces, porque querías una librería en C++, mejor dicho, para que
sí,
corriera más rápido.
sí, básicamente, para poder utilizar sistemas más grandes
Venga, y
de
hay una
desarrollo.
cosa de puro aficionado. Y si hubiera tratado con esta de Julia, que
Eh,
usualmente tiene fama de que lo hacen, que compiten ahí con C++ en algunas cosas numéricas.
Ahora mismo, yo en particular, en lo que hice en Canadá fue con esta librería de acá, con DMRG, pero lo hice con
Ujú,
métodos de 2 dimensiones. Entonces, hay una forma para hacerlo de, de dimensión más grande, pero no me atreví a hacer el benchmarking aún, pero estoy seguro de que al hacer, hay una cosa como bien curiosa, y es que no llegué a hacer el benchmarking de este contra la mía. Debería ser en performance un poco parecido, sino que un poquito peor, porque no está siendo como powered by NVIDIA, es decir, no hay CUDA en esto. Entonces
ujú.
puede que en contracciones tenga un buen algoritmo, pero nada en contra de lo que ya está previamente establecido en ULAS o en otras librerías de manejo de matrices en C++, porque ya tienen muchos años y la gente,
Ujú.
los computer scientists que han trabajado en eso, pues ya lo tienen muy bien establecido ahí.
Ok. Bueno, no sé si alguien más del público quisiera hacer una pregunta o un comentario, ¿no? Mm, si no es el
Pues,
caso. Ah, Alonso, dale,
mira,
dale, tranquilo.
no, una cosita. Eh, o sea, yo entiendo, por ejemplo, que una de las cosas, bueno, por ejemplo, con Matrix Product Stage, ¿no? Que uno puede, si uno está cerca, digamos, un punto crítico, puede empezar a implementar como una especie de proceso de renormalización, agrupando, pues, como las matrices, ¿no? O sea, multiplicándolas, y a partir de eso identificar, digamos, de las componentes principales de de la matriz agregada, como la estructura, hemos dicho, como ciertas propiedades estructurales del estado fundamental. Y yo me pregunto, pues, ¿eso es posible hacerlo acá también? O sea, lo han mirado, por ejemplo, analizando, digamos, situaciones cerca de, no sé, transiciones de fase o algo así.
No, eso es el próximo, porque acá solamente estamos implementando lo de Matrix Product Operators, a ver si está dando los mismos resultados que con
Ujú.
Matrix Product States. Pero definitivamente, si se puede hacer con Matrix Product States, se puede hacer acá con Matrix Product Operators. Es solamente una extensión, pero también se puede hacer lo mismo el cálculo por ejemplo, el algoritmo este de DMRG, también se puede hacer con
Ujú.
Matrix Product Operators. Simplemente es como contrayendo estos tensores de acá y haciendo la optimización de un tensor singular y luego haciendo eso en toda la red. Entonces sí, se puede hacer también.
Ok. Chévere, muy bueno.
Bueno, ok, entonces, pues muchas gracias de nuevo, Juan Sebastián, un gusto tenerte. Ah, Karen, adelante, gracias.
Hola a todos. Qué bueno estar por aquí. Y a veces me gustaría estar más, pero pues desafortunadamente a veces no puedo. Pero bueno, hoy Juan Sebastián nos puso un trabajo que en realidad vale mucho la pena resaltar, que fueron 2 chicos de pregrado quienes introdujeron el MPO al MPS viejo que teníamos. Un poquito acerca de la pregunta de Alonso acerca de las transiciones de fase y los puntos críticos. Son 2 cosas un poquito complejas. Eh, Numéricamente hablando, las transiciones de fase cuánticas, utilizando Tensor Networks, pues estos ejercicios de Tensor Networks eh, son, son bastante buenas de, de clasificar, de caracterizar, de encontrar, de ubicar en el espacio de fase. Mientras las fases involucradas sean fases con gap. Es decir, realmente acercarse a un punto crítico, entendiendo
Sí, sí.
una fase crítica como una fase gapless, es complejo, porque numéricamente hablando, digamos, el compu no puede diferenciar entre diferentes estados base que están al mismo nivel. pero pues digamos que lo que hace la gente es tratar de acercarse a esos puntos críticos como engañando al computador. Desde el punto de vista de transiciones de fase entre cualquier tipo de sistemas que por alguna razón abran el gap, por ejemplo, sistemas finitos, siempre abrirán un gap, así sea una fase gapless en el límite termodinámico. Entonces, por ejemplo, esa fase dimer que habló Juan Sebastián es una fase que en el límite termodinámico es doblemente degenerada, pero que numéricamente hablando para sistemas finitos, pues el gap se abre dentro de estos dos ground states y uno siempre termina cazando alguno de los dos. Pero pues ese es uno de los poderes que tiene estos Tensor Networks, que solamente es cuestión de ingeniarse qué tipo de medida podría hacerle yo a los estados para detectar la transición de fase. Solamente es esa, y aquí pues ese es el poder del MPO, que cualquiera que sea el operador que uno se imagine, puede implementarlo. Ese es el potencial que tiene el MPO, hacer de los operadores algo más tranquilo para manipular. Que pues previamente era el poder del MPS, hacer del estado una manera más tranquila de manipular, pues ahora es con el MPO, que es brutal.
Y una pregunta, o sea, yo me acuerdo que con los MPS pasa una cosa cuando uno está acercándose, por ejemplo, al punto crítico en una de esas transiciones gapless, que entonces que el bond dimension diverge pues con la longitud de correlación, ¿cierto? Como, eh, no sé, creo que hay unos criterios como de unas entropías de Rényi o algo así, no recuerdo bien. Eh, y aquí, pues, mejor dicho, en este caso con los MPOs también pasa lo mismo, o sea, o hay...
Ya, lo que pasa es que el MPS tuvo la gran ventaja del MPS es que el estado tiene una saturación o cuasi saturación en la entropía, ¿sí? Y eso es lo que le permite a uno poder hacer un truncamiento en el tamaño de las matrices y ahí, ¡pum!, ese es el poder del MPS.
Cuando uno no
Pero,
está exactamente en el punto crítico.
exacto, en el punto crítico, entonces es que la entropía no satura o cuasi satura. Y entonces por eso es que el MPS tiene problemas, ¿sí? O desde el punto de vista numérico, que es difícil que el compu minimice y encuentra dos mínimos iguales y dice, bueno, ¿y cuál me quedo? ¿Cierto? O salta de mínimo en mínimo y uno no puede realmente decidir cuál es el estado base. Y nunca termina convergiendo. Pero en el MPO no es para los estados, es para los operadores. Entonces, en el MPO es una forma de escribir el operador. Es una manera de escribir el operador como un producto de matrices. Entonces, allí el MPO en sí mismo no está supeditado a nada más, sino a la estructura matricial que mostró Sebastián. No tiene restricción alguna adicional en cuanto bueno, no sé, como el estado tiene restricción por entropía, que el operador tenga restricción por otra cosa.
Pero entonces el input del estado mismo, pues como sea, de las condiciones que definen el estado, pues vienes a través de...
Del MPS. Es que aquí el estado se escribe como MPS, los operadores ahora se
También,
escriben como MPO.
ya, sí.
Mientras que antes, cuando el MPO no existía, o sea, en mi época que el MPO no existía, lo que hacíamos con los operadores era pues darnos la pela y hacer unos operadores horribles, grandísimos y sobre todo acarrear ese operador sitio por sitio o dos sitios por dos sitios. Entonces, por eso tener mediciones de operadores no locales como una correlación, pues es un dolor en el cuello, porque entonces, por más poder de cómputo que uno tuviera, pues estaba muy, muy limitado. Esa limitación es la que viene a solucionar el MPO.
Ya.
Esa es la cosa. Ujú.
Ah,
Entonces, claro, las
Bueno,
puertas se abren mucho con eso.
pues bueno, muchas gracias a Karen y a Juan Sebastián y a sus compañeros ahí del grupo. Nos da mucho placer tenerlos por acá. Nada, antes de despedirnos y darles de nuevo las gracias a Juan Sebastián, les recuerdo ahí a todos que aquí están, pues estamos siempre recibiendo buenas charlas que nos quieran contar. Este semestre nos quedan 2 o 3 fechas más, les estaremos confirmando, por lo menos 2. No sé si nos alcance para la tercera. Y bueno, iremos ahí como hasta la primera semana de junio. Después todos nos iremos a descansar o a hacer buena física en otros lados, que supongo que por eso es el tiempo. Y nos volvemos a reunir en agosto. Entonces, no, de nuevo, gracias. Yo siempre termino estos lunes aquí muy contento, me gusta. Y nos vemos la próxima vez. Y gracias, Juan Sebastián. Muchas gracias.
Gracias a ustedes por la invitación. Gracias, Alejandro. Y